Awesome, thank you. So welcome to Less Boring Tests, an introduction to property-based testing. I'm Wes. I work as a database engineer, which is a mix of database administration and automation. Before that, one of the things I did was that web application development. This talk is about something I picked up and used heavily during that time. So property-based testing is a technique I discovered a couple of years ago. I was a couple of weeks into a new project, which is a great time to try anything. I gave it a go and it found a bug in my code. There was a bug in my code, and this code already had tests. Finding a bug in some code that already had tests was enough for property-based testing to impress me. I fixed the bug and I carried on using it. I liked it so much, I ended up using it for the majority of the test suite and the rest of the project. Property-based testing is not something that's particularly well known, which is a bit of a shame because I think it's a really useful technique. The goal of this talk is to get more people to try it. I'll introduce the techniques and concepts and provide some tips and tricks to make it easier to get started. Warning, this talk contains a lot of code. Most of the examples are in C# because that's what I'm most familiar with. The property-based testing library is available in many languages though. I'm using XUnit as the unit testing framework and fscheck as the property-based testing library. Let's start with the most common way of writing tests, the boring way. We'll start with a couple of examples I nicked from Microsoft because one, they're representative of what's demonstrated and taught out there, and two, I couldn't be bothered writing them myself. These tests are for a simple .NET to-do API for a to-do list application. They cover a couple of test cases for the getToDo function. Our first example is getToDo returns not found if not exists, or as I like to call it, to-do1 is not found with empty database. The test has three parts which I've helpfully labeled. We have arrange, act, and assert. First, we spin up a new empty database, and then we try getting the to-do with ID1. We then assert, we get a not found result, and we've proved we can't retrieve to-do1 from an API with an empty database, which is great, except we only have an empty database once, so it's not really representative of the actual use case of our software, where our database has data in it. Next, we have what they've called getToDo returns to-do from database. In reality, is getToDo1 returns to-do with ID1. This time, we create a test to-do with ID1 and a test title, description, and isDone property. We insert it into our database. We call getToDos with ID1 and retrieve a to-do. Then we assert that the to we get back has an ID of 1. We ignore the other properties we dutifully filled out. Hopefully title, description, and isDone are the same as our original test to-do. We call these example-based tests. We pick an example, hardcode the data into the test input, and then we assert that the output values match what we've pre-calculated. I'm going to call this the boring way. Who enjoys writing this sort of stuff? Nope, doesn't look like anyone else does either. Cool. I can write one or two and then I've had enough. Unfortunately, test suite requires a little bit more than that. The boring way has a few issues. The first is I don't like doing it. And I don't want to do things I don't like doing. Writing tests when you don't want to do them can be an exercise in resentment. Who wants resentful tests in their code base? If I'm bored, I'm going to be less engaged and I'm less likely to do it well. I may miss some test cases. It's tempting to do the bare minimum that's required to get a pull request approved, rather than what's required to actually ensure our software has high quality. Handwritten test data favors oversimplified tests, which isn't representative of what our software is actually doing. How many of your users are Mr. Testing McTestface from 123 Test Street, Exampleville? You have to balance test cases that can be easily read and understood against more complex test cases, but useful for finding bugs. It's a lot of work to write a comprehensive test suite in this way. You have to come up with a large corpus of examples, and then you might have to hand calculate results for all of those. A large suite of very similar but slightly different tests invites copy and paste errors. Attempting to apply deduplication by factoring out distinct data or set up boilerplate into common test functions adds a layer of indirection and obfuscation. It can also unnecessarily couple tests that should be distinct to each other. Humans are bad at doing complex, repetitive tasks with a high degree of quality, which is why we automate stuff. There's a different way, hurrah! Property-based testing is another way of writing tests. It eliminates the need to manually create test data and is written in a style that is more similar to programming. Property-based testing is a generative testing technique. The tests use generated test data rather than specific examples. Each test checks that a property holds for a system under test, and given inputs of characteristic X, we can expect behavior with characteristic Y. The tests generate data in search of counterexamples where the property doesn't hold. If it doesn't find any counterexamples, our test passed. Properties are just rules that describe the behavior of a system. The general form is, for all inputs like characteristic, when precondition holds, property is true. This is a bit academic. Let's have a look at an example. Let's start with a simple example, an order function. Order takes an input sequence and creates an ordered output sequence from it. Order has two key properties. The first is that the elements of the output sequence are in order. And the second is that the output sequence maintains the elements from the original input sequence. Elements are in order. This is a property that gives order its name. A sequence is ordered when the element at index n is less than or equal to the element at index n plus 1. We can test that every element in a sequence is less than or equal to the next. Here's an implementation of a test for the elements are ordered property using the fscheck library. For each test case, fscheck generates an arbitrary array of ints and passes it to our test function. Inside the function body, we order the sequence, and then we check whether it's ordered. Instead of calling assert functions, we just return the result of our check. The test runner takes our property, generates the values, and executes the test for all of them. We can see here that it tried 100 test cases, and they all passed. Here's how we stop ourselves getting away with just returning a static ordered list by verifying that the output sequence actually has the same elements as our input. Most of the test remains the same as the previous one. We just change what we're checking. There's a few characteristics that set property and example-based tests apart. Example-based tests have hand-generated test data, whereas property-based tests will use a pseudo-random set of data. We verify values when we're doing example-based testing compared to characteristics with properties. Example-based tests have one test case per test you write. Occasionally, you could have many pieces of data feed into the same test case, but you still have to write out each piece of data individually, compared to the hundreds we get from property-based testing. Every test run of an example-based test suite will use the same data, whereas you'll get different data on each run of a property-based test suite. The writing experience of example-based tests is like data entry, whereas property-based tests, it's like programming. And example-based tests are boring. Property-based tests are less boring. Okay, let's take a quick look at the test boilerplate to get ready for the example. Here's the standard structure of a test. It's a function that returns a property. We decorate it with the property attribute which registers it with xunit. Xunit has fscheck integration, and xunit will use the fscheck test runner to run the test. There's a couple of other ways to declare a test, but I'll use this form because it gives us the most control and it has the nicest test runner integration. We'll use this form with prop for all to generate our properties. Properties are the building blocks of property-based test suites. Each test run checks the properties in our suite. We can compose properties together using logic operations such as and, or when. Properties also have decorators we can use to give this test runner more informative output. Let's learn by example and see how to construct a simple property-based test suite from scratch. We'll walk through implementing and testing FizzBuzz. FizzBuzz, everyone's favorite programming challenge. FizzBuzz is a simple counting game to teach children division. Somehow, it's also been adapted to test programmers. Let's work through it rule by rule. Let's ignore fizzing and buzzing for now and start with the base case, stringifying the original number. This is our first property. For all integer inputs, we get back the original string representation. We'll call the test returns original number. We can rephrase this as for all arbitrary integers. We use an arbitrary int to provide the test data for prop for all. Let's take a look at arbitraries. Arbitraries are what provide the test data for our properties. Property-based testing frameworks include a number of default arbitraries for common types. They can also generate them for user-defined types by using the default generator for each member. An arbitrary wraps a generator, which generates data, and optionally, a shrinker, which does failure case simplification. Let's ignore shrinkers for now and have a look at generators. Generators generate the data an arbitrary provides. The most basic generator aims to produce a uniform selection of values for a type. Generators can also sample from an array or a set of values, create lists, or return the same thing over and over and over and over. The libraries include a number of primitives we can use to make our own generators. These include functions we can apply to the generated values to transform existing generators into new generators. fscheck has a collection of default arbitraries. The arb map contains all the registered arbitraries. In this case, we'll use the arbitrary for ints, which will produce positive and negative integer values. We can use arbmap default arb4 int to retrieve it from the arb map. Now that we've covered the input data, we can look at the testing we get back the string representation part. This part of the property is the testable. The testable is what gets evaluated for each generated value. This is a function that takes the type produced by the arbitrary as an input. It can take a few forms. It may return a Boolean to indicate success or failure, have no return, and throw in failure, or it could return another property. Our testable here is a simple lambda that takes an int x, calls FizzBuzz with it, and returns whether the result of that calculation is equal to the result of x to string. The FizzBuzz implementation for this requirement is pretty simple. We just call toString on the input. Now that we have a test, we're ready to move on to our second property. Let's add a new requirement. Multiples of 3 return fizz. Here's a test for this new property. First, we need to generate some multiples of 3. Here's where we create our first generator. We extract the generator from the default arbitrary for ints. We apply a transformation to the generated values by calling select x maps to x times 3 to multiply each originally generated number by 3. We then rewrap it in a new arbitrary with arb from gen. We could have also routed to the nearest multiple of 3, but this method is simpler and gives us more distinct values. Changing the requirements has caused the original test to fail. After 6 tests, we found that our property does not hold for the value 6. It also doesn't hold for the value 0. Let's add a label to see what's going on. Labels are shown in the output of failing properties. We can write a wrapper for the equals operator to add a label that prints the value of the operands. The test now shows that buzz does not equal 0. Returning buzz rather than 0 is the expected behavior of this test. So let's fix the test. We're going to fix the test for the new requirement. We can do this by excluding multiples of 3 from the test data. We can add a filter to restrict our arbitrary to only values that satisfy a condition. Here we're adding a filter that filters out all multiples of 3.
Sorry, can you tell me again why you're doing that?
Basically, the test here is failing for any multiple of 3, but for fizzbuzz, we don't want to get a number back for a multiple of 3, we actually want fizz, which is a requirement of our second test. So we're filtering out of the first test because the first test needs to deal with numbers that aren't multiples of 3. Filters throw away generated data. The process goes like this. You generate an arbitrary value, you run the value through the filter. If the value satisfies the filter, you can use the value. If it doesn't satisfy the filter, you start the process again and generate another value. Because this process discards data, we'll generate more data than we actually need. If a filter is overly restrictive, it's possible to exhaust the data generation before we have enough test data to run all our test cases. Sometimes it's a better idea to apply a transformation to the arbitrary to turn an invalid value into a valid one. We'll introduce a new rule. Multiples of 5 return buzz. We'll also create an accompanying test. Our test contains some common logic to generate an arbitrary multiple. Let's factor out the creation of a multiples generator and an arbitrary. I like to split custom generators and arbitraries into separate functions because we may want to use the generator separately from the arbitrary to create other generators. This saves us from having to extract it each time. Let's update the implementation, and we'll run our tests again. And we get 2 test failures when we run the tests. The first is the same thing that happened last time. We also need to filter out multiples of 5 from our first test. The second test failure discovers a gap in our specifications. Some multiples of 3 are also multiples of 5, but we haven't specified what the behavior should be for that case. Specs can have bugs too. The cool thing was we didn't have to write anything explicit to catch that error. It was naturally discovered within the values fscheck generated. Let's fix the specification by adding the last property of fizzbuzz. Numbers divisible by both 3 and 5 return fizzbuzz. We add this new test case to complete the test suite. We also filter out multiples of 5 from the multiples of 3 test and multiples of 3 from the multiples of 5 test. Now we have a basic fizzbuzz implementation and a suite of passing property-based tests. We can confidently refactor without having to worry about regressions. Hooray, all our tests passed. Okay, let's go over what we've seen. So we've got the basic test boilerplate. Each function has a property annotation and returns a property. We use prop for all to bind an arbitrary and a testable together to create a property. We can use the arbmat to retrieve arbitraries. We apply a filter to the arbitrary to restrict the value that gets tested for the property. We added a label to customize the failure output. And we created our own arbitrary by transforming a custom generator. So far, we focused on properties. We've looked at how they're composed of arbitraries and testables. Next, let's look at test execution and examine how tests are run. Each test run follows some basic steps. It begins with choosing a seed from the random data generator. Then we generate an arbitrary value and evaluate the testable with it. If the testable succeeds, we increase the size, generate another value, and increase the generation and testing process until we've run enough test cases. The first step is the seed. Property-based tests generate pseudo-random test data. Each test has a seed which controls which data gets generated. Each test run will use a new seed unless you manually specify a seed. The output of the failing test will include the seed that was used for that test run. This allows us to easily reproduce a failure. Here's the output of the failing test, including the seed. We specify the replay parameter in the property annotation down the bottom there, and we'll rerun the property with the same seed. That will use the same data that were generated last time. This is helpful with debugging. You get to see the same failure each time, so you don't have to deal with the conditions changing on you when you rerun. It's also useful when the property doesn't fail on every run. You can pin the test to a failing case, or if the failure happened during a CI run, you can use the same seed to debug it locally on your machine. The other parameter that affects what data gets generated is the size. Size controls the complexity of the generated data. Sizes help us manage the trade-off between easy debugging and simple bug reproduction, and finding bugs that require more complex data to trigger. If we just stick to simple examples, we may not find all bugs. A buggy sorting algorithm may work for smaller sequences. A function that uses floating point numbers may not run into precision errors until you start using much larger numbers. Smaller sizes produce simpler values, and larger sizes produce more complex ones. This can be things like drawing samples from a larger range of possible values, longer sequences or strings, and the inclusion of more varied characters. Here's 10 samples from the default generator at the sizes 1, 10, 100, and 1000. We can see the larger size generated within values within a bigger range. For integers, the size will set the absolute value of the minimum and maximum possible value. Sizes start small and finish large. The first test execution will start at the minimum size. With each check, the test runner will incrementally increase the size until the maximum size is reached on the last execution. You can set the beginning and ending sizes for a property, or scale the sizes in a generator. You can also generate arbitraries that always sample from the full range of a value using the do not size wrapper. End size defaults to 100, which may not be enough in some test cases. However, the best way to generate integers in a specific range is the choose generator. So far, we've looked at custom int generators. Let's come back to our to-dos API and look at custom generators for more complex types. We'll implement a generator for a to-do, and then re-implement the original to-do test using the property-based testing. Here's a generator for a to-do. It's almost equivalent to the default generator fscheck would generate for us. Title, description, and isDone are populated to the default generators for strings and booleans, respectively. We're going to leave the ID field default initialized to a value of 0. This is because to-do is an entity type, and the database will set the identifier when it tracks it. We're using the link query expression syntax. There's a method chain equivalent, but it isn't particularly readable. We derive a value for each object member we want to generate using the from value in generator form. Each of our values is independent, but we'll have a look at values with interdependencies in a moment. Now that we looked a little at custom generators for objects, let's use it to re-implement the original to-dos test. As a reminder, here's what the original test looked like. The test attempted to retrieve a to-do by ID. To do this, we did an ID for a to-do that does not exist. There's a few options we have for doing this. We could use an empty database and choose an ID greater than 0, which is what the original test did, but it's not very useful. We can choose a ID that's greater than the number of values that have been added, This makes assumptions about how IDs are generated. It would be better if we didn't have to make those assumptions. Or, the option, adding data, letting the database populate the IDs, followed by deleting a to-do, and then using its ID. We have an ID that could plausibly exist within our data, but we know it doesn't exist because we've removed it. Let's use that option. Here we have a generator with a dependency between members. We generate a list of to-dos and the index of one to delete. First, we populate our database with the to-dos we've generated. Adding them to the database will populate the IDs. Next, we take the one we want to remove and we delete it. The ID will no longer be found. And then we attempt to retrieve it using the ID and verify it's not found. We'll stick with the xunit asserts functions. The throw and failure, which will fail our test, will also get some object formatting for free. We can adapt the not found test for the found case. This time, we just select the to-do without deleting it. These tests aren't that different to their original example-based versions. We're just using generated data rather than hard-coded examples. We had to solve the small problem of how we generate usable IDs. It takes a few more lines to write a generator compared to some hand-coded data, but it's worth it because you can reuse the generator multiple times. A good way to ensure that a generated data fulfills the right preconditions is to write tests for your generators. Here, we're testing that our multiples are multiples of a multiplier. If you have well-tested generators, you can then compose them to test more complex scenarios. Let's take a look at properties and the sorts of things you can test. In most cases, properties will be the rules of your system. User information is retrieved, a submitted order is created, invalid registration details are rejected. Observable side effects. Actions that change the system state have side effects we can observe after. Some operations will change the state of an object. Adding an element to a list will increase its length. Creating an entity will add data to the database we can retrieve and validate. The test can perform an action and then check that the system state has changed. Frequently, we have a set of invariants that should hold before and after a function, so we can test for preservation of invariants. Our ordered sequence still had all the elements from the original sequence. Filtering doesn't affect the order of elements. Code formatters don't cause semantic changes to the source. We can check the invariant still holds after we apply our function. Round trip. Many operations have an inverse operation. Sometimes an operation may be the inverse of itself, like reverse. Common pairings are serialization and deserialization, encoding and decoding, encryption and decryption, and endpoints that will create entities and endpoints that will retrieve them. We can apply the operation, then its inverse, and check that we end up with the original output. Round trips can be useful for testing parsers. You can start with the abstract syntax tree, generate a source representation from it, parse it, and then confirm that the parser produces the same syntax tree as what you started with. Matches a test oracle. Test oracles are functions we can compare our results against. This is common when we have a naive implementation that's unsuitable for production code. Or some oracles may only be correct for a subset of values, but we can still use them to verify that our actual implementation is correct across that range. The property is also useful when we're replacing an existing implementation and want to ensure that we're still producing the same results as we originally had. Metamorphic relation. Metamorphic relations are changes to input that don't cause a change in output. We apply a transformation to the input before we feed it into a function and still get the same result as the unmorphed version. Here, we shuffle a sequence before ordering it. and validate that it has no effect on the output. You could test a speech or image recognition algorithm by adding small amounts of noise, changing the volume or contrast, shifting colors or pitch, or adding and verifying that the result is still the same. You could test a parser by adding non-semantic characters, such as additional white space, to an input prior to parsing. Idempotent. Idempotent functions will give us the same result regardless of how many times we apply them. Examples include getting absolute values, filtering, getting distinct members, trimming white space, and other reformatting. We may test for idempotence to ensure the correct handling of multiple delivery. We can also check that the result of the first application is different to our original input, but we have to be careful of the identity case that causes a function to be a no-op. Induction. Structural induction is where a problem can be broken down and defined in terms of a smaller version of itself. Many recursive problems have this property. The classic example is a sequence like Fibonacci, where the next term of the sequence is defined as the sum of the previous two terms. We can also verify a base case, then recursively check the next step. For example, we can verify that a tree is ordered by checking that all of its subtrees are ordered. I used this property when I was writing a compounding interest calculator. Calculating the next month from the previous one was equivalent to calculating the balance from the beginning. There's also mathematical relations that may sometimes apply. Association, where changing the grouping of operations has no effect on the result. Two forms of commutation, where changing either the order of arguments or changing the order of operations has no effect. Distribution, where separately applying an operation to the parts when joining them is equivalent to joining them and then applying the operation to the whole. Identity, where some values have the same input and output. Zero, where some values give a zero output. And one, where some values give a one output. This can be useful for nailing down base cases and forming a basic sanity check. Let's come back to shrinkers. Falsifiable after 5 tests, 2 shrinks. Let's look at what that means. The purpose of a shrinker is failure case minimization. Shrinking attempts to find a simpler counterexamples that still cause the test to fail. A shrink function takes a failing test case and returns a sequence of values to try next. They're passed until the test body until either 1, the property fails for the new example, or 2, the sequence runs out of elements. For failures, the failure case is passed to the shrinker, and the process repeats. It's important to ensure the shrunk values has the same characteristic as the values for the generator. A shrinker for an even number generator must not return odd numbers. We'll see an example of the shrinker for an arbitrary multiple. Each shrink is one less multiple than the previous one, and we'll stop shrinking at 0, which is a minimal value. Shrinkers only get used when a test fails, so it may not be worth always writing them. Sometimes it's easy just to fix an issue with the original failure case you get. Here's an arbitrary for a multiple of a number that includes a shrinker. The shrinker takes the original multiple and produces an enumerable of the multiples that are smaller than it. In this case, the smallest multiple is 0, which is 0 times our original multiplier. The shrinks interpolate between the original value and the 0 in steps of the multiplier. Each time we shrink, value is 1 multiplier less than the previous value. For example, if the multiplier is 5 and our original value is 20, the shrinks will be 15, 10, 5, and 0. Every shrunk value is still a multiple of 5. You can test shrinkers too. Unfortunately, property-based tests aren't the one true way. You will still need to write some example-based tests. The random sampling methodology may not find some edge cases. The data generation is unintelligent. It will randomly try values from its sampling space. This is great when the behavior is consistent across a range and we can confidently generalize from the values we check. However, if your search space is large, you may not randomly hit a small subset of it that has divergent behavior. Imagine looking through many parts of a haystack, but not finding the needle. You can solve this by increasing the number of test cases or tweaking the size. In most cases, you'll have to write generators that have the characteristics the test requires. If your system has a boundary of cases delineating different behaviors, it's useful to divide those sections into separate properties. You can test that the behavior is also different on each side of the boundary. Your property-based testing library and testing framework may not have native integration. You might have to write some tooling to encapsulate the property-based tests or inject data into the setup. I had to do this with Angular and FastCheck. Property-based testing libraries are available in many languages. The Wikipedia page for the original QuickCheck library has a list of languages and libraries that's way too big to reproduce here. David R. McIver, an author of the Python property-based testing library, Hypothesis, blogged some recommendations for libraries in many languages. The blog post is from 2016 though. Some of the choices may no longer be the best. However, it includes their evaluation criteria, which is still useful for choosing a library today. Let's recap on why we want to do property-based testing. It's generally infeasible to test every input and output for a function. Therefore, our tests must sample a subset of the input space. We can write out a small number of examples by hand, or we can use property-based testing to randomly sample many values. Choosing property-based testing allows us to try more inputs and reduces the manual bit. If we sample more of the input space, we increase our chances of finding bugs. I'd like to acknowledge the use of some MIT license code from the Microsoft.NET samples repository. I also used some images from pngimage.com, which are licensed under Creative Commons Attribution Non-Commercial. There's a number of people I'd like to thank. The presentation was built using Reveal.js, which was written by Hakim El-Hattab, Kurt Schurthard, author of the FSCheck library. Thanks to the DDD committee for a great job they do putting on this conference. They also provided speaker training, which was really helpful. Shout out to the volunteers. They do awesome work on helping to run things. I'd like to thank the people who listened to part of this talk as I was writing it and provided feedback. I gave an earlier version of this talk for the Bankwest developer community. Thanks to the committee for giving me some practice runs and feedback. I'd also like to thank the DDD sponsors. DDD is an awesome conference, and their support makes it possible. Here's some of the references I used when assembling this talk. Anyone looking to take a photo? All right, let's move on. Johannes Link and Hillel Wayne both have blogs with good posts on property-based testing. Johannes has a series on applying property-based testing with a focus on Java. Hillel's blog includes some ways in which you can extend property-based testing. Let's take some questions now.
If anyone would like to ask a question, I've got a microphone for you.
How much is the overhead involved in writing property-based testing as opposed to normal testing? Because most of the time, you need to sell testing to most projects.
Okay. All right. I've not been in an environment where you need to sell testing. These are the tests that go with the code that go in your pull request. And if your pull request does not include tests, your colleagues will just say, hey, no way, I'm not looking at this. Write some tests, please. Verify that your functionality is correct. I think it's probably similar effort to writing tests the old way, or you might spend a similar amount of time on it. You'll just redirect your effort in different ways. But I think you get more out of it investment for your investments. You can be more confident in your software and still spend the same amount of time. So Sorry, I can't help you selling testing to people, but I don't know, not having software that doesn't, having software that doesn't break is great, so I'm not entirely sure why people would be against that. Like, nobody enjoys using stuff that doesn't work.
Got another question over here.
Hi, thanks for the talk. You rely heavily in reflection and link, so I wonder if performance is ever an issue.
I've not found performance to be an issue in practice. For the stuff I was working on, you could do a full build and deploy pipeline in under 10 minutes, which was fast enough for me. I think it's going to be slightly slower because you are running more tests compared to if you write them out by hand. But I think a lot of the overhead is sort of in like spinning up the test cases individually. And so you may actually pay that performance less because you test more data within the same test, I guess, if you want to put it that way. So I haven't found performance to be an issue in practice. If you start hitting those problems, you probably want to look at doing something source aware where you say, hey, I changed these parts of the application and every test case that's touched by this is all of these. I'm going to run those. These are tests for something that doesn't interact at all and I cannot run them, and use that as a way to optimize your performance. But
Any other questions? Alrighty. Wes is going to be here all day. Happy to have a chat.
yeah, I'm not active on social media. Oops. So there's nowhere to follow me. Please come find me later if you want to have a chat. Thank you.